we have been trying to define the energy of the gravitational field in analogy with what we do for classical electrodynamics or quantum electrodynamics. And the problem with gravity is that from the field equations you get a conservation condition which is covariant, but to prove that some charge similar to this one is conserved, in that case it would be the for momentum, you need a conservation of this form, not of that form. And so to achieve that result you have to split the field equations into their contribution to the lowest order around some background, flat space in our case, plus the rest, and the rest you move to the right hand side, and that will be the contribution, the gravitational contribution to the energy itself. And so you get something that is conserved. So the Riemann tensor in the expansion around flat space is given by these two contributions, which also have to be expanded around flat space, but we can neglect that. And so we have written the Einstein tensor this way. And it is convenient to collect the various contributions into this kind of divergence, because the Q rho nu is anti-symmetric, and so the conservation of this is manifest because of the symmetry in the partial derivatives and the anti-symmetry in these two. So what can we do now? We can write the for momentum, p mu, in a convenient way. So p mu is equal to the integral on space of what? Our t mu 0. I recall that we have defined t this way. That is to say, it's the right-hand side of the equations once you expand around flat space and you keep only the first order to the left-hand side. T mu 0. And that is equal to what? T mu 0 is 1 over, so it's, yes, I forgot a kappa squared here. So T mu nu is 1 over kappa squared of this object y. So we get 1 divided by 2 kappa squared, this thing. 2 kappa squared partial rho q mu nu rho and 0. So the upper index is 0, nu, and d3x. So this can be written as 1 divided by 2 kappa squared partial rho q mu rho nu sigma nu, where sigma, I recall, is equal in this case we can, well, we are in flat space, so we don't even have the square root of g. and that is equal to epsilon nu alpha beta gamma dx alpha dx beta dx gamma divided by 3 factorial. This d3x when nu is equal to 0, because if we are integrating on R on space, then necessarily alpha, beta, and gamma have space indices, which brings nu to be 0, and therefore you get what we had before. This is in a nicer form, because now we can treat it as a differential form and show that it is the integral of an exact exterior derivative of a form. So this is a 3 form, because sigma nu is a 3 form. We will write it as the derivative, exterior derivative of a 2 form, which will not be globally defined, and so there will be a contribution from infinity, from the boundary of R3, and that is the energy as seen from the radiation to infinity, similar to what we did with QED when we wrote this thing. The charge is equal to the integral of a total derivative, space derivative, and therefore it is a contribution, like in Gauss's law, from infinity. So we can do the same for gravity. And how to do that? This is 1 divided by 2 kappa squared, r cubed. And now we play with epsilon tensors in a way similar to what we are accustomed to doing. Rho nu, let's say lambda tau epsilon, lambda tau psi zeta, and then sigma nu, which will be epsilon nu alpha beta gamma dx alpha dx beta dx gamma 3 factorial. Now we adjust a factor in front. So we just inserted these 2 epsilons, which have 2 contracted indices, and so they are equal to -2 delta rho nu delta rho psi delta nu zeta minus the anti-symmetric part. So that gives a factor, since there is anti-symmetry in rho and zeta inside Q, we have 2 equal contributions. So that is a -4 times the result we had previously. So which means that we have, oh, I forgot a minus sign here, because as usual, this is not d3x, but minus d3x, because I recall epsilon 0, 1, 2, 3 is equal to -1. So when we do that, we get a minus. Oh, I forgot to cancel a little bit of things. So epsilon 1, 0, 1, 2, 3 is equal to -1, which means that here you have minus, and then you divide by -4, so you have 1 divided by 8. As usual, at this point we contract the two other epsilon tensors, the ones that have one common index nu, and that will give a certain determinant. So 1 divided by 8 kappa squared, integral on R3, partial rho Q mu psi zeta. Then we can copy the third epsilon tensor lambda tau psi zeta. And then we have a determinant, since nu here in second place and there it's in first place, we have a minus sign. Since two epsilons give a minus sign, in Minkowski space we have two minus signs, so we have a plus. And then we just copy the various indices, rho, lambda, tau, rho, lambda, tau, rho, lambda, tau, alpha, beta, gamma, alpha, beta, gamma, alpha, beta, gamma. And then we have dx alpha, dx beta, dx gamma divided by 3 factorial. Okay, so let's see what we get from here. That's very easy actually, we don't need to do anything now because this thing is multiplied by an object that's already completely anti-symmetric. So from the determinant we have how many terms? We have 1, 2 times 3, so 6 terms, but they are all equal because this is anti-symmetric in all three indices. So you just drop 3 factorial and alpha beta gamma will become rho lambda tau. So in the past we only had 2, so we had to work out a little bit of the determinant, the anti-symmetry in 2 indices, but now it is in 3, so it's straightforward. So the 6 factorial goes away, and you have 1 divided by 8 kappa squared, integral on R3, partial rho q mu psi zeta, and then you have dx rho, dx lambda tau, dx lambda dx tau, epsilon, lambda tau zeta, psi zeta. And now you see that this is an exterior derivative because you have dx rho partial rho. So that we will write as, well, first we write it as 1 divided by 8 kappa squared integral r cube. That is the exterior derivative of this object. Well, then we give a name to this form and write 1 over kappa squared integral of the total derivative of the 2 form q mu, which is defined as 1 over 8 q mu psi zeta epsilon lambda tau psi zeta dx lambda dx tau. And then integrating by parts, using Stokes' theorem, this will be the flux at infinity, the surface of this q mu. So you have an integral on a surface at infinity, which is the energy that is radiated to infinity. And theorem, positivity of the energy, P0 is non-negative in the synchronous gauge. Which means that G mu nu is equal to 1, 0, 0, 0, 0, 0, 0, Gij. And the field bind similarly. And this theorem is the proof is very involved. We will not do it because it would take 8 hours. 2 years ago I did it, and this proof is due to Nestor in the form that's more economic, but there have been previous proofs which were even more complicated by Witten, Yao, and others. The point is that I want to stress, however, is first that when you want to define the energy in gravity, you need to deal with a specific reference frame. Not only, you need to deal with a specific gauge choice, because the only proof that exists today, apart from being very involved, it is done in a specific gauge. And that is, by the way, not the most convenient gauge for many other purposes. So that makes you wonder what the energy truly is in gravity, and maybe the problem is still to be considered still open rather than solved. We have already seen also that in gravity, if you want to define observable quantities, which means gauge invariant quantities, invariant under diffeomorphisms, you cannot take a scalar field for example, any scalar field is not an invariant, although one says that scalar is invariant. It is not really an invariant because it does transform. And what you need to do, so let's say that this, let's not call it small phi because that could be confused with scalar field. This is any scalar, just any scalars, like the Lagrangian density, for example, square root of minus g times the Lagrangian. And you have to integrate it. So that means that you have a non-local observable. Local means that it depends on one point. It's located at one point. Phi of x could be, for example, a mass term, could be the kinetic term, those are scalars built with a scalar field here, but you can build them with whatever you want. With fermions, these are local objects, local observables. They are not observable in gravity. They depend on the reference frame, so have to be careful with the terminology. they become invariant only once you integrate, and that means that they are non-local. So in gravity you can have observables, but they are more complicated than what you normally do in other theories. And the energy is, of course, a reflection of that, and much more actually. It's maybe even more complicated, but we have to deal with that, because that is a fact. So you can also, some people want to see gravity as a spontaneously broken theory, because anytime you expand around flat space, you can view this as a vacuum expectation value of the metric, like the Higgs has constant plus fluctuation. And then you break general covariance down to Lorentz invariance, because every truncation of this expansion is no longer invariant under the complete symmetry group or the theory, every truncation. But the theory is invariant, of course, because when you spontaneously break a symmetry, it is always, the invariance is always there, even if it's not manifest. But the vacuum is not invariant. And so the vacuum breaks, the choice of vacuum breaks the symmetry down to a subgroup. Now we start talking about quantum gravity. And today, to move forward towards that, we review how a simple diagram, a simple Feynman diagram, is computed with the simple example of a scalar field, because once we clarify some things that you do not even find in textbooks, actually, it will be easier to generalize and see what you can do that was missed. So the diagram is very simple. It's this thing. It's called bubble diagram. And the reason why we study it is that we have a unitarity equation, which we have already considered. And the unitarity equation can be expressed in the form of so-called optical theorem. IT are the Feynman diagrams, amputated diagrams. And when you insert S equals 1 plus IT into this equation, 1 plus IT, 1 minus IT dagger, 1 plus IT, then you have 1 plus IT minus IT dagger plus T dagger T. And that is equal to 1. So if you simplify 1, you have IT minus IT dagger equals minus T dagger T. Or if we want, we can multiply by minus 1. So we have minus IT plus IT dagger equals T dagger T. and that is also equal to T divided by I minus T dagger divided by I. And that is twice the imaginary part of T. T is known as amplitude, IT is the Feynman diagram. So twice the imaginary part of T is T dagger T, which is non-negative. And this is the optical theorem. We have already checked that the Feynman prescription for the propagator satisfies the optical theorem. That means that you put an I epsilon here, and then you can take the vertex you want, minus I lambda. We can imagine here a 3 vertex with 3 legs for the bubble. Could be 4, could be 5, could be whatever you want, but the diagram we compute is always the same, because some integral here. It doesn't really matter what coupling constant we put in front, so we can assume that the coupling constant is equal to 1. And we have checked that twice the imaginary part of, so not the diagram, but T is the diagram times minus I. Put I on the other side. So if you put here the minus I, this was indeed equal to pi delta p squared minus m squared, which is non-negative. And why is this important? Well, so this is important because it's unitarity. So unitarity should hold in any theory, in particular in quantum gravity. And you can ask, well, it holds. Why should we worry? The problem of quantum gravity is not unitarity. The problem is that it is a non-renormalizable theory. So the problem is renormalizability. It can be shown that the Einstein theory, and maybe this I didn't mention, Einstein, the Hilbert action plus all the infinitely many corrections that you need to add to subtract the divergences. If you remember, you have to consider an infinite set of terms, all the ones you can construct. That theory is unitary. So that could be a theory of quantum gravity. So that theory is a theory which has cosmological term, let me call it lambda c, not to confuse it with a cutoff. Then the Hilbert term. Then, well, if you remember, look, you can put this to 1 here now. Okay, let me call it lambda. We don't have a cutoff around, so For us, it's not important. And then, if you remember, we have infinitely many terms that we can organize all of them as being at least cubic in the Riemann tensor, but we can eliminate everywhere the Ricci tensor. So the convenient way is to classify them by means of the Weil tensor. So this theory is unitary, which means that it contains infinitely many terms, but it doesn't disturb the unitarity. So it contains infinitely many independent coupling constants. Should that be a problem? Not necessarily, not at low energies, because at low energies the two important things are the ones that have the lowest dimension. The other infinitely many couplings become important at high energies, and they may never be important for us. So one could be happy with this theory for billions of years, probably. But if you ask yourself if quantum field theory left the door open to go beyond this, then the question is to make the theory renormalizable, but the simplest attempts you can make will destroy unitarity. So that's why we have to discuss unitarity. Why is that? Because if you want to make the theory normalizable, you have to improve the behavior of propagators at infinity. Which means for large momenta. And the graviton propagator goes like 1 over p squared. That's not enough to make the theory renormalizable, because power counting then leads to a Newton constant that has negative dimensions. But we remember that if you consider instead a higher derivative action, like this one, put some parameters here now. We organize it this way. Should I remember if there is a sixth here? No. R squared, where zeta, alpha, and psi are positive, and this is written in this combination because it's equal to Weil squared plus a total derivative. So it's convenient to, you know that Riemann squared can be written as a combination of Ricci squared and R squared up to a total derivative, and so Weil squared also can be written as a combination of Ricci squared and R squared, this combination up to a total derivative. Well, this theory higher derivative theory is renormalizable why? Because now the propagator here there are two derivatives in R, but here there are four derivatives in Ricci squared. So the propagator behaves much more nicely for p squared large. And that's enough to make Newton's constant dimensionless. And the other parameters that are there is a redundant parameter. There are too many, but it's easier to put a constant in front and keep all the other independent. Otherwise, you would have to choose 1 to 1, but there is no privileged choice for high energies. You could put this to 1. At low energies, you could put that to 1. So the theory is renormalizable, but what about unitarity? In general, when you add higher derivatives, you have a problem with unitarity because you have a propagator that goes like p squared squared. So let me write a generic polynomial. I already factorize it like that. If you have a propagator like this that falls off more rapidly than 1 over p squared at p squared large, then you can decompose it in the difference of two simple poles. And remember that the simple poles are the degrees of freedom and the residue is important. Have this identity. And that means that one of the two poles will have a negative residue and the other will have a positive residue depending on which mass is larger than the other. So necessarily one pole has a negative residue. But you cannot have unitarity with the Feynman prescription and changing the sign of a propagator because of this identity. If you have a propagator here, and if you change the sign of that propagator, you will change the sign here. But the optical theorem, therefore unitarity, tells you that the right-hand side is non-negative, t dagger t. So what can we do? Let me insert some states. Let's say we have a Fock space. We are expanding around flat space, so we will have Fock space. We call it W. And you have, let's say, alpha or AB states belonging to W. So in terms of states, you have an identity written like this. These are the in and out states. And so that is equal to alpha T dagger T beta. Fine. Let me insert a completeness relation here. Now, let's see one problem with unitarity. So, if you want to study whether a higher derivative theory is unitary or not, higher derivative theory will have this kind of propagators. And that means that you have these minus signs. These minus signs tells you that in your Fock space you have some in and out states that cannot be consistent with unitarity because, well, there are many examples where you can violate this identity, but the simplest example is this one. You just take that propagator. If you take that propagator, you will have two delta functions instead of one. This is the usual propagator like this, so you have just this. In that case, you will have pi delta p squared minus m1 squared minus pi delta p squared minus m2 squared. So have a difference of two delta functions instead of just one delta function with a positive sign. And the difference of two delta function cannot be non-negative. So we can do it. Say yes. So let us do it. Probably it's better to let's see. Yes, there is room enough to do it here explicitly. So if now you take this propagator, you will get what? You will get pi divided by m1 minus m2 squared times delta of p squared minus m1 squared minus delta of p squared minus m2 squared. And that is if we use the Feynman prescription. Maybe it is better to make room for this before moving on. we will move later. So if we use the Feynman prescription, what does it mean? We write the propagator as 1 divided by p squared minus m squared plus I epsilon. Times p squared minus m2 squared plus I epsilon. And we can redo the computation. And you will have nothing, it's the same coefficient. Okay, so if you use this propagator, you violate unitarity. It is not non-negative. But that's the problem of the Feynman prescription, you could say. That's not the problem of the theory. Before the prescription, before you give the prescription, there is no theory. It's just a classical Lagrangian, and unless you give a set of rules to quantize it, it remains a classical Lagrangian. So, what is the problem? The problem is that in your Fock space, you have wrong states. So, if you write down the optical theorem by means of states like that, in and out states, you could say, why don't I restrict? Oh, let me see. Okay, you can stop now. Why don't I restrict the set of initial and final states to the subspace of the Fock space that does not contain the wrong ones? You cannot do that because this equation, the unitarity equation, is quadratic. Here there is some linearity in T. Here it is quadratic. So you can restrict alpha and beta, but you will not restrict what's in between here. That spans the entire space, and so you will regenerate the wrong states in between. And you will not be able to prove this identity. Because remember, we assumed unitarity and we derived this identity. But you will not be able to prove this identity with these kind of states. What you can prove is an identity which is called pseudo unitarity. So it's an identity like this, minus IT beta plus alpha IT dagger beta. That is equal to this sum T dagger N, and then there can be a minus sign or plus sign, depending on whether your intermediate state is physical or unphysical. And the sign is this sign here. So this is called pseudo unitarity equation. Which means that this sum is not a completeness relation. You cannot say it's equal to 1 and drop it, and so you cannot derive the unitarity equation, the optical theorem, and therefore the unitarity equation. And this is because of this minus sign. Again, you can restrict the set of initial and final states alpha and beta to whatever you want, but you cannot restrict what's in between, and so that's not a completeness relation, and so you cannot go from there to the optical theorem and the unitarity equation. Let's stop 10 minutes.